Okay, so I needed to get this information to you real quick before the exam tomorrow. I apologize that this wasn't especially clear in lecture. You may have noticed it for those of you who did the reading and then as you did your Mastering Chem, but I just want to make this 100% clear because it's some easy points that you'll be able to grab tomorrow. So first of all, I want to draw your attention to this table from your book, talking about the molecularity of collisions and relating them to rate law. And notice that for elementary reactions, or the subsequent steps in a reaction mechanism, but primarily the elementary reactions, that the molecularity is basically the order. And so if you have a unimolecular collision, then it's going to be first order. If you have bimolecular, whether it's two of the same molecules colliding or two different ones, that's going to be second order overall. And termolecular is going to be third order overall. And so that's basically part of collision theory, that the degree that the concentration affects the reaction rate is largely going to depend on, well, how many of these do we have to have hitting at the same place at the same time with the right amount of energy. But again, remember, this only applies to elementary reactions. All right, so then let's look at that as how it works with within a reaction mechanism then. So the only type I'll ask about tomorrow is one of these. We're going to talk later after we've established equilibrium. We'll talk about how to do more complicated situations, but the only one you'll have to know about tomorrow is a mechanism where the first step is the slow step. And so if it has a slow initial step, then we can look at that initial step and determine something about the overall reaction rate and rate law. Notice in this one that in the first step, which is, we're told, the slow step, and by the way, you don't have to be able to recognize that from anything other than if I showed you a graph, it would be the one with the higher activation energy, obviously. But I'll literally probably tell you this step is slow. And in this case, you've got two NO2 molecules that need to collide in step one in the mechanism. And so that's going to obviously be second order. Now, notice in an elementary reaction or in a step of a reaction mechanism, which are elementary reactions, the coefficients in the balanced chemical equation will tell you the order. And so in this case, both NO2s have coefficients of 1, and so each of them are first order for a total of second order. And so the rate law is simply that the rate of the reaction, or that first step, is the rate constant times the concentration of NO2 squared. Now, again, that's squared. You can look at it two ways. One, you can think of it as, well, I've got an NO2 with a coefficient of 1 and another NO2 with a coefficient of 1. And so NO2 raised to the first power times NO2 raised to the first power gives you NO2 squared. Or you can think of it as, well, it's second order with NO2 because you have to have two NO2s colliding at the same point. And so either way, you get second order in NO2. That's the only reactant, and so therefore it's second order overall, and that's your reaction, your rate law for this reaction. Again, it's very important to remember that this only applies when it's a slow first step, which is the only one that I'm going to give you tomorrow. But you need to combine these two concepts to be able to grab a couple of points on the exam tomorrow. If you have questions, I'll be there early tomorrow. Otherwise, keep studying, and we'll see you tomorrow.